Thank you, Chan Chan. Shout out to DAF for hosting this great event. Shout out to all of our various sponsors. Super excited to talk about Iceberg v3's deletion vectors, aka row-level deletes. My name is Aniruth. I'm currently a product manager at Databricks, and we're going to start with the history of row-level deletes back in Hive, before Iceberg, give some context on what we're trying to accomplish here, and then work our way forwards through each iteration of Iceberg to where we're going to go in the future with deletion vectors. When I first started learning about this topic, it was really weird. If I told you that you couldn't delete something, it feels very awkward. It feels almost like you don't believe me when I say that. If you open up any Excel file, a Google Sheets spreadsheet, you can delete any row, any column. No one ever asks you any questions about what's happening. So I want to actually start, before we even Hive, why exactly would we even consider spending any time about row-level deletes? And the answer has to do with how large-scale data storage works. These things called data lakes. Data lakes need high scalability and high throughput. So they're typically built on object storage as opposed to a typical file system that we might use. A good way to think about it is you have a bunch of buckets, and you can arbitrarily add and remove buckets as you need to. Your files can be located wherever you want on the buckets, and that allows you to build these really, really high-scale systems. The context, though, is that if you want to get any individual file, you have to go via some API proxy that will decode what bucket you need to actually access. So an example here is I have some Iceberg file that's located in bucket number 5. So I go to the API proxy, and that tells me exactly where I need to go. The API, though, is somewhat limited. As a result of this lack of hierarchy that allows us to scale somewhat arbitrarily, we're only really allowed to do a few operations. And the key operations here are that we can put an object, we can get an object, we can delete an object, and finally we can list objects. It should feel somewhat limited because these limitations are in part of why we actually get the scalability that we do with object storage. So it's not as simple as just adding a new API. Further, if you think about how you actually delete a file on some file system, so pretend you were SSHing into another server. Typically what you do is you actually list the files and then you figure out what you want to delete. But in this system with object storage, it's actually a little challenging because you don't have the hierarchy anymore to help you do lists efficiently. There are ways around it and there are optimizations, but it remains a fundamental limitation. Additionally, there's also this question of what exactly a partial deletion means. If I want to delete one row, you can notice here that I'm using this word object, which is really just a bunch of bytes. It's not a specific table, and there's no defined exact way in an object store to delete just a portion of something. There's no real definition of what that means. So you can already kind of tell that this concept of a row-level delete is starting to get a little hard. And to spoil some of the surprise, the way we get around a lot of the limitations with object storage is via this thing called Iceberg. I don't know if anyone's heard of it in this room, but it's this system where we have a tree-like metadata structure to track data files over time. Okay, no one reacted when I said, I don't know if anyone's heard of it, but I think everyone raised their hand when Chan Chan asked. So someone definitely knows. So hopefully this looks familiar, where we have this Iceberg catalog that stores the current metadata pointer, and then we're able to access all of our Parquet data and delete files to do our actual reads. And this unlocks a lot of great stuff like asset guarantees, scalability, APIs, and especially row-level deletes bolded here. So given all this context of why this might even be a problem, let's go back to Hive and talk a little bit about Hive did deletes. And the short answer here is I didn't really do deletes. What do I mean by that? It means that if you want to delete a given row, you end up deleting the entire partition. And it's very common that you partition your data actually by dates. And so it becomes a problem where you end up having to drop an entire day just to delete one record. And for many business use cases and use cases in general, this is unacceptable. And so you're forced to end up recomputing the entire partition of what it should be yourself so that you can drop it, figure out the new partition, and then add the new partition in yourself. I'm seeing some heads nod. If you've ever done this, it's very painful. And to give you an idea of just how painful, we can take a look at all the steps that are required, where you basically do exactly what I described. And to make things even better, this is not ACID compliant, which means that if you have any concurrent jobs accessing a given partition where one is deleting something and another is inserting, you have signed yourself up for 12 hours of no sleep. It's worse than on-call, and it's a terrible experience. So given all of this context, Iceberg v1 now steps into the picture. And we introduce this concept we call copy on write. The key idea here is that we're going to address the deletions by just generating a new copy of the data file without the deleted rows. Now this will also be ACID compliant because we're going to leverage the Iceberg commit pattern where we generate all of our data files or /delete files as needed, but we haven't got to the delete files yet, but you can pretend it's part of the same commit structure. And then you generate all of your metadata. And at the very end, at the last step, you try to go to the catalog and do an atomic commit. So you don't run into these issues where multiple people are trying to access the underlying same data files, because it's actually very rare to actually delete a file directly. Let's do an example of how copy on write works. Let's say I have some arbitrary table, and we're just looking at the first 5 rows within this. If I want to run a command to delete rows 2 and 4, I simply generate a new copy of this file without those rows. And this new file gets saved and tracked in the latest Iceberg metadata version, and I do the update via the catalog. The problem is that we're rewriting this new file and we're invalidating the old one, which is pretty expensive. If we think about how this scales with the size of the actual table that you're deleting. It doesn't scale with the number of deletes that you have. And so if you have a lot of records and tables, which is very common because the whole point of doing this is for really large scale storage, you start to run into performance-related issues and compute-related issues. So now we go to the next step, Iceberg v2, which tried to address this with the concept of positional deletes. The way that we address this is something called merge on read. The key idea here is that instead of generating a new file like we did with copy on write, we're just going to store the deletions as a file directly. Iceberg v2 has 2 different variations of Parquet delete files. The first one is called positional deletes. The idea here is that you calculate what positions in a given file you want to skip. The alternative is an equality delete, where instead of calculating the position at write time, you instead generate a more broad category. For example, maybe where ID equals 5. And in that scenario, at read time, the engine then has to do the work of taking this equality delete file and figuring out where to delete. So the trade-off here between the read and write time, that Iceberg gives you the flexibility to decide how you want to represent your deletes. For the purposes of this talk, I'm going to focus on positional deletes, just because that's the one that we've evolved into deletion vectors. Equality deletes remains the same and is unchanged in Iceberg v3 compared to Iceberg v2. Like I did with copy on write, I'm now going to do an example of how merge on read works. Let's say again we start with a table, the exact same table, and we focus again on the first 5 rows. We're going to run the same delete operation on rows 2 and 4, and this time we create a new positional delete file. To be very specific, it is a Parquet delete file, which is going to be relevant soon. And this way, we can now track the deleted rows, or the indexes of 2 and 4. When we now go to read, we then see this, where we see the original table, we then see the delete file, and then the engine merges them at read time, hence the name merge on read. And then we just skip rows 2 and 4, hence why they're annotated as being deleted. This leads to no rewrites, and we also have 2 ways to group these positional deletes. The first one is we can scope them at the partition level, which means I create one file for all of the given deletes that affect a given partition. And the alternative is a file scope delete, which is now the default in Spark 3.5 and the latest Iceberg 1.8 that targets Java. The issue, though, is that now there's a trade-off on the number of delete files you have. As you can imagine, merge on read makes this trade-off where we're delaying the cost of the rewrite, where now on read time, you have to account for all these delete files. And if you have one per every single file, and maybe you're doing a bunch of different deletes, you start accumulating a lot of really tiny files. And they start adding up and imposing an IO tax and penalty every single time you want to make a read on these tables. So to solve that, typically you do compaction, where you take a bunch of these small delete files and you create a big delete file, or you might as well just combine the actual delete files with the old large Parquet file and effectively run a copy on write every once in a while. And that improves your performance going forward. I've spent all this time talking about how the Parquet delete file works, but it turns out that engines don't actually understand the Parquet delete file directly, and the engine level representation is actually entirely different. Let's start from the basics. There's this concept of a bitmap, where we're going to go ahead and store a bunch of indexes by using a map of bits that correspond to those indexes. So it's very useful for bitwise operations, which is why we're going through all the penalty and the stress of trying to figure out this kind of operation, where if I want to union or do any intersections with sets, it's very simple because you can just do it bitwise. And a lot of processors and computational techniques these days are optimized for those kinds of operations. Here's an example of what that would look like, where you have a bunch of indexes laid out, and you have a bitmap where one corresponds to indexes 0, 2, and 4. And so what that means is that those are now existing in this given set. We then take this a step further, and we introduce this concept of roaring bitmaps, where the idea is bitmaps are really space intensive. If I want to store a bitmap for 0 to any n, I have to store a bit for every single number, even if all the numbers are 0, which means that there's no deletes. The problem with that is you start spending a lot of unnecessary space on these bitmaps, even if they're super great because of these bitwise operations. And so this concept of the roaring bitmap came into play, where we're now going to start playing around a little bit. We're going to say we have some 32-bit number, and we're going to start chunking them. So we're going to chunk it apart into 2 pieces. The first, we're going to take the most significant 16 bits. So these are the 16 bits on the left-hand side of the number, and we're going to call this some key. And then we're going to take the remaining 16 bits and group these all into containers by the key. The idea here is that we can actually leverage the cardinality, which means the number of unique elements in a given set, on the container, and then we can figure out the best kind of container to use. So the key idea here is that we're going to use bitmaps when it makes sense, and when it doesn't make sense, we're just going to use arrays. And then we also have this other concept of what's called a run. A run is a group of consecutive numbers. I have an example that goes through this, but the run length encoding is actually very important to prove that roaring bitmaps are the best way to compress these kinds of numbers. It's actually a paper that goes through a lot of detail. The original paper doesn't include the run length encoding and is like, I want to say like 10 pages long, and then they introduce it and it jumps to like 25 pages and it's like the same underlying topic. So the actual bitmap is just a bunch of numbers like 1, 0, 1, 0, 0, so on and so forth. Then we throw in our sorted array. This is the classic way to just represent a bunch of indexes together. This is the alternative where you don't have a lot of cardinality. And then the third option is this run length encoding, where if I have some numbers like 11, 12, 13, 14, I can just encode that as 11, 3, and it does the same idea. So I've spent all this time talking about roaring bitmaps and the engine level representation, and it sounds nothing like what I talked about with the Parquet delete files. And if that's what's going through your mind, you're exactly correct. We have this representation mismatch between what's happening in the engine and on disk. So engines use the roaring bitmaps. And the reason is, like what I was talking, you get all these great benefits of this set-like operations done bitwise, which allows you to vectorize your operations across many rows of data at once. However, it's different than how deletes are stored on disk as your Parquet delete files. And so your engine ends up playing this game where it's playing catch between your disk and your memory on all these given writes and reads, and it imposes a penalty and an overhead every single time. And you might be asking why. Why would anyone choose to ever knowingly make this decision and approve the Iceberg v2 spec? Well, the honest answer is we're now going to get a little bit more deeper into the details and talk a little bit about how we're going to implement this for 64-bit numbers, which wasn't clearly defined at the time, and it was only defined for 32-bit numbers. So instead, the Parquet delete file was chosen because Parquet is a format that can be read by any engine. So there's no issue with how you're actually saving the serialization of the binary blob that compromises the roaring bitmap. That's a handful of words. The key idea that I want everyone to take away from this is just that there's a representation mismatch. What you save on disk is different than what the engine needs. With that, let's now go into the third phase of Iceberg v3, deletion vectors. So I want to start by highlighting what are the key problems and how we're going to improve this to give almost a forecast of what we're about to discuss. The first one is what I just talked about, this overhead due to the difference between on-disk and in-memory representations. The second one was about the trade-off between file scoping and partition scoping, where it affects the number of delete files you have, but then also with the partition scoping, you're loading delete files that may not be actually relevant to the files that you're trying to read. You just happen to be accessing that partition, and now you pay the penalty of loading everything. And then finally, we also talked a little bit about this maintenance procedure, where you have to compact your delete files to avoid there being too many. And there's some issues with that because the maintenance procedures are entirely optional, which means that you may run into scenarios where it may not be optimal to have that many delete files. So to solve these, Iceberg v3 introduces a couple improvements. The first one is this concept of using the roaring bitmap for both on-disk and in-memory representations, which addresses our issue with the overhead and difference between the representations. The second one is we're going to use file scoping for all delete files. This one sounds a little weird because it feels like we could have just done that in Iceberg v2. There's no reason why not. And I hear you saying, well, okay, the problem with that was we had too many delete files. And so what we're going to do with this third thing is we're actually just going to force synchronous maintenance on write. And so we're going to shift the burden onto the engine when it's doing the write to compact these delete files together so that we can guarantee that there's one deletion vector per file per snapshot going forward to ensure good performance. Let's now construct a deletion vector and actually understand what's happening at the binary level of the blob. So our goal here is to store a non-negative 64-bit number in some bitmap. We can optimize actually for 32-bit positions and leverage the 32-bit roaring bitmap that was clearly defined by splitting again the first 32 bits into a key and then using a roaring bitmap for the second 32 bits on the sub positions. The idea for why this is useful and why we don't just use a 64-bit roaring bitmap directly is that the expectation is that most of your numbers will be inside where all of the key is going to be 0. With 32 bits is a lot. 2 to the power of 32 is a very, very big number, and it's hard to get to that many indexes consistently. So this allows us to save space, but gives us the flexibility to add more bitmaps if we ever need to. So we start out with some length. This is the first 4 bytes within our blob. We then introduce some magic bytes. We then actually do the roaring bitmap, and we call this the portable format to explain the fact that we're accounting for 64 bits and not 32. And then finally, we have some checksum to just verify that we have the right bytes. And then additionally, expanding on that, we have some arbitrary magic bytes that I've isolated here if you're curious. And then we actually have the roaring bitmap, where you can see that we have this key setup of 4 bytes, which is the first 32 bits. And then we actually have the bitmap in however much space we need based on how the roaring bitmap ends up working. We also store the number of 32-bit bitmaps, which is useful if we, for some reason, violate that earlier assumption and our keys are not just all zeros, and we actually have a lot of numbers. We are flexible enough to account for that. So this is the deletion vector blob. This is the actual binary ones and zeros that are on disk and in memory. The way that we actually store them, though, in Iceberg is via this nice thing called a puffin file. So puffins are great because they can store arbitrary blobs and things that don't really make sense to go inside the Iceberg metadata manifest tree. So these just contain arbitrary information, and one of the great things that they contain is this thing called the deletion vector v1 blob type. And so very similar to what we just saw, we're now stacking all of the deletion vector blobs on top of each other. There's a footer at the bottom which includes some information about where exactly to go if you want to access some deletion vector. And it also tells you what data file it references and the cardinality of how many indexes are included within that deletion vector roaring bitmap. You'll notice also that the same deletion vector blob that we talked about on the previous slide is what we're stacking up on top of each other. So now we're starting to build the pieces, and there's one more final piece that we have to build, which is the actual delete manifest that now goes inside the Iceberg metadata tree. And the reason why we want this is because we want to use this as a pointer to go exactly to the deletion vector blob. We want to avoid this issue that we had with partition scoping, where we load the entire puffin file and then have to find our deletion vector. Instead, we're able to leverage the delete manifest and go to the correct position inside of our puffin file to get the roaring bitmap that we want. So we again have our dvs.puffin file that includes all of our blobs stacked on top of each other. And then we have some delete manifest, typically in Avro, where we have some contents and some file paths, and it tells us where to go to get our actual deletion vector. And the nice thing is that when you go via this actual this delete manifest, you'll have these arrows that tell you exactly where to go to get your blobs, so you can avoid having to go into the footer of the puffin file and then jump around to find what you need. It's a small optimization, but it's one that matters a lot. And this is what goes inside the Iceberg metadata tree, so when your engine's trying to access a roaring bitmap, it follows this path. I now want to start talking a little bit about how that maintenance procedure works now that we've actually built up the actual deletion vector blobs. In Iceberg v2, engines got to choose when they're going to compact delete files. But the issue is that compaction is always an extra cost incurred by an engine, and it's sometimes hard to justify because it's not directly related to a current write that's happening. So it makes sense that sometimes you're going to try to push that off for as long as you can and hope that it happens. Iceberg v3, though, enforces that you have at most one deletion vector per data file per snapshot, which is now a write time requirement to ensure good performance going forward. And the nice benefit of this is that Iceberg v2 position deletes now have an easy path to be upgraded, where Iceberg v3 can read those Iceberg v2 position deletes, but once you write something with an Iceberg v3 writer, it'll go back, find all your positional deletes, combine them, and then give you one nice deletion vector blob to use going forward. So it's a nice almost migration path if you really think about it. So I'm going to now go through an example of how this works, because I realize that this sentence, at most one deletion vector per data file per snapshot, gets a little confusing when you start thinking about time travel and you want to account for different deletions at different moments in time, but still make sure that they are valid. So we start out with creating some file with a number of rows without any DVs. We then create another snapshot where I'm going to delete ID equals 1. We create some deletion vector. I'll call this dv1. That is just storing ID equals 1 inside of the roaring bitmap, probably using some array because there's so few. We then go ahead and add ID equals 5. Technically, this would create a new Parquet data file and make the it really made the diagram complicated, so I'm just going to pretend like we just added into the original table. And 1 still remains deleted using the original deletion vector. And this is the key part where now we delete ID equals 4. And now in Iceberg v3, when we delete ID equals 4, we create a new roaring bitmap stored in this new deletion vector blob that contains both 1 and 4. Iceberg v2 would have only contained 4, and then you would have to go through and figure out ID equals 1, ID equals 4, and do the work yourself of having multiple delete files. So if you take a look at this, we're able to time travel. So I could go back to snapshot 1, snapshot 2, read the table at those moments in time. But at any moment, when I'm trying to actually read the table, there's only one deletion vector blob that I actually care about. And so we're able to hit our performance requirement and still be fine. And then finally, oh, that's a scary word, Delta Lake, inside the Iceberg talk. One thing that's worth calling out with the deletion vector blob is that the formats, we believe, should not silo data. And as a result, Delta actually uses the same binaries for the deletion vectors. So it actually goes down to the exact ordering of the bytes, right, where we use big endian values for length and the checksum fields, as well as little endian values for the actual roaring bitmap itself. That's a little handshake going on. So I want to conclude this talk, I think I'm about a minute over, just talking a little bit about the summary of deletion vectors that we discussed throughout this talk, just because we've discussed a lot of things. And if I have to leave you with anything, it's just these 4 things, where we started out with our Hive-style deletes, where you dropped and you added a replacement partition and did your best to figure out what should be deleted. We then went to this copy on write method, where you rewrote the Parquet data file without the deleted rows. Then we went to this position delete method, where you write the Parquet data files, partition or file scoped. And then we finally concluded with Iceberg v3, where we're now going to use roaring bitmaps directly and enforce compaction to solve some of the problems we ran into. And we encourage you to join the Iceberg community today.
Cool. That was very interesting. Does anybody have any questions? Oh, of course.
Hopefully these questions aren't too hard.
Going back to your previous slide with the 4, what were the magnitudes of performance improvements that you would see going from each?
Yeah, so that's a good question about what the magnitude of performance improvements you would see across each. So going from Hive to anything else is huge. When you go from Iceberg, so to be very clear, the copy on write method is still supported inside Iceberg v2 and Iceberg v3. The difference is that most of your workloads are not going to be deleting enough files to the point that you want to have copy on write as your default. It's often better to set deletion vectors or Parquet delete files as your default. You can think about it as a reasonable improvement on most workloads, especially on you can think about it almost as your BI workloads, where maybe you're deleting a few rows at a time. You're going to see a very noticeable improvement. If I'm being totally honest, the representation is kind of a small overhead because most engines can kind of figure out how to make that transition. Especially once you actually load the data file and you start doing your operations in memory, you really start to notice the translation between on-disk and the in-memory representation with the bitmaps, only when you're actually persisting files. So if you're just doing a bunch of operations in memory, you won't actually notice that difference, so the difference decreases. I said a lot of words. The simple way to think about it is as you go down, the order of magnitude decreases.
So the puffin files you talked about here, is it different from, I think earlier there was a stats related puffin files as well, right? So those are 2 different things here, that gets written to a metadata folder.
I have no idea what you're talking about with the stats file.
There's the S3 Iceberg table that creates a stats and then stores a puffin files.
I don't know anything about S3 tables, and I'm not an authority to speak on that.
Okay.
No, there's an Iceberg table with the puffin files with this table.
That stats files, is it same or is it different?
Yeah. Well, so to clarify, Puffin is just an Iceberg file type that's used to score. It's technically called a sketch, which is just information that's broadly useful across a bunch of files. I want to clarify that I'm not saying I don't want to make a statement that is specific to how S3 tables works, that it does or does not support that, because I'm not familiar with any such limitations or guarantees that S3 tables offers. I feel like I'm at a press conference, just being very precise.
A little bit. Okay, we'll take one more.
Thanks for the great talk. So performance of the V3 looks lucrative, right? But is this a one-way door, the migration from V2 to V3?
Yes. So there's backwards compatibility in the sense that Iceberg v2 deletion like files can be read in Iceberg v3, but there's no forwards compatibility in the sense that once you write a roaring bitmap, the Iceberg v2 engines will not understand what that is, even though it's funny because the actual engine understands it. So it's kind of a weird thing.
So basically, let's just theorize, right? So I'm using the V2, and then I want to move to V3. So I move all my, say, writers to V3. So I have a puffin files from now on. And then say, from this time, I need to make sure that all my, like, say, whoever uses Spark to write that has the V3 support on. Otherwise, it's going to be not supported. Because the way I understand it, like the Athena, Trino, they already do that. They already support puffin files. But like arbitrary Spark job that I'm running should support it. Otherwise, I won't be able to read it, right?
I think I follow that. I want to like restate in my own words just to make sure. So if you have some writer that is now Iceberg v3, and let's say you had like a bunch of tables that are all Iceberg v2, the first time you commit a write using an Iceberg v3 writer, on that snapshot, it will go ahead and create a new deletion vector blob. So even if you understand the puffin file format, you need to make sure that all of your readers understand the deletion vector v1 blob type that can be stored inside of a puffin file, which is a slightly different thing that is adjacent to the puffin file understanding, right? Like I can understand a puffin file, but then if a new type like deletion vector v2 or v3 or something was added as a blob type, I may not understand that. So basically what I'm saying is once you write to it with an Iceberg v3 like writer, you need to make sure that anything that's reading it has support to understand the deletion vector blobs, and then you're good going forward. I would encourage you to think about it as like the deletion vector blob requirement and less about the puffin requirement. Okay, thanks everyone.